Hi Chem 212 students, and welcome back for our third and final lecture this week about acids and bases. As we finish up this chapter, we're going to talk more about how to predict the equilibrium position in a reaction. Remember that the reaction will go from the stronger acid and base towards in the direction to the weaker acid and base, or in general, chemical reactions go from the less stable reactants to more stable products. And so in terms of a stronger acid, that's indicating a less stable molecule. It wants to give away its proton. So if we're comparing relative acidities, we've been doing this the whole chapter. We have two ways to do it. If we have the pKa values, we can compare the pKa values. Lower pKa value, stronger acid. If we don't have the pKa values, we can use REO on the structure of the conjugate base and determine which would be the more stable base, and thus that would be a weaker base. It's stable, it doesn't want to grab a proton, and thus its conjugate acid would be a stronger acid. So here we have an example of an acid-base reaction. What's going on in this reaction as we go forward? And I'm going to indicate forward with this red arrow. As we go forward, what's going on is you can see that this nitrogen is grabbing a proton, and this nitrogen here is giving up its proton. And so what that means is this nitrogen is going to attack this proton, make a bond, and then a lone pair will be left behind. And that's how we get the structures here on the right. Now, if we're going in the leftward direction, which I'll use the blue arrows to indicate the mechanism, this nitrogen here will be attacking this hydrogen, and then that will leave a lone pair behind here, and that will produce this structure. So now we want to see, this here, if we're labeling these, this is in the forward direction, this is the acid, and this guy here is the base. And then on the right side, we have the conjugate base of the acid, and here we have the conjugate acid of the base. And so here are our bases. Okay, so this is the conjugate base of this acid. The more stable this structure is, the stronger of an acid this will be. So we want to, and then here for this conjugate base of this acid, again, the more stable this structure, the stronger of an acid we'll have over here. So let's consider the stability of these structures. In order to do that, we're going to have to use REO. And when we do this, we're going to need to consider the atoms. We also have to consider the resonance. And there is resonance here because we have allylic lone pairs. So we can have the two arrow pattern that we saw in chapter 2. And that will produce a structure that looks like this. There will be a double bond now to the nitrogen because this lone pair made the double bond. This double bond will now be gone, and those electrons will be a lone pair on the sulfur. And there's still one lone pair on this nitrogen. Over here, we also have a resonance form in which we have a similar situation, but it's an oxygen ion that has a negative formal charge. And the double bond there. Now, when we compare these, remember when we're comparing atoms. So now at this point, everything's the same except for the atom here. And so we want to know which of these two atoms will stabilize the negative charge. Remember, as we go horizontally on the periodic table, the more electronegative atom will stabilize the negative charge better because it will hang on to those electrons and keep them. However, if we go vertically on the periodic table, the larger atom will stabilize the negative charge by spreading it out, similar to the same reason why resonance makes a structure more stable, because it spreads that negative charge out. Remember the refrigerator magnet example, right? That spread out charge is not as sticky. The very localized charge, more sticky. More reactive. It will go and stick to something and try to steal atoms and react with it. So here, the more stable structure, this one is the more stable one, and this one is the less stable one. So more stable, less stable. So what that means is that this acid here will be a stronger acid because its conjugate base has a more stabilized negative charge. So in terms of our two acids, this is the stronger acid. And this is the weaker acid. And likewise, we can talk about their conjugate bases. The weaker the acid, the stronger the conjugate base. So this is a stronger base relative to this base, which would be the weaker base. And so the reaction is going to go from the stronger acid and base to the weaker acid and base. So the reaction is going to be favored on the left side. And so this reaction will have more reactants and less products when it's at equilibrium. And so now we're just, using the same REO system that we used before, but we're just now applying that to predict which side of the reaction will be favored. Remember, reaction will go from the stronger acid over to the weaker acid, or the stronger base over to the weaker base. Now, if we got pKa's, our job is a lot easier here. So we got two acids here, HA, which is just a generic acid, here being the acidic proton and some rest of the molecule. And then we have the conjugate acid of the base. So what's going on in this reaction is the H plus is being given over to the base. This is not a mechanism. This is just, hey, H plus is moving. Okay, and so the H plus attaches here and you get HB. And technically this would be HB plus and A minus, even though they aren't written. But we can see that the pKa of HA is lower than the pKa of HB, the conjugate acid of the base. And so HA is the stronger acid, HB is the weaker acid. So this reaction is going to move in the forward direction, from the stronger acid to the weaker acid. So you can see that's significantly easier to do when you've got the pKa's. But if you don't, you can use REO to compare the relative strengths of the acid and base. So from stronger acid to weaker acid, stronger to weaker. Okay, so now let's consider here, and I want to, whoops, I'm gonna get rid of these. I wrote on this earlier. Oh no. Okay, I'll get rid of these for a second. All right, and so another important concept here when talking about acids and bases is if you want a particular base, like these are all bases, consider these bases. If you want it to react as a base, well, you're going to have to react it with a stronger acid, an acid that is stronger than its conjugate acid. Okay, for example, the conjugate acid of this base would be this one here. Okay, and this is where I attach an H plus over to this carbon right here. And so in order for this reaction to go, we need to react this base with an acid that is stronger than the conjugate base of the acid, because this is what will be on the product side. We need this to be the weaker acid compared to the acid we're reacting with this. Here's another example here. This is a carbon with a negative formal charge. It has a lone pair and two hydrogen atoms attached. And so its conjugate acid would be the one where an H plus attaches right here. And so the conjugate acid would be this one. And there's just going to be these three hydrogens, but usually we don't draw them. And so we need any acid that is stronger than this conjugate acid of this base. Likewise here, the conjugate acid would be if we add a proton onto where the oxygen is, so that would make it OH, and the charge would no longer be negative because it got the H plus there. And then for this one, the conjugate acid would be if we attach a hydrogen here to this oxygen, and then this one would be a positive formal charge. Okay, so all we need to do is to choose appropriate reagent for these bases is to choose an acid that is stronger than the conjugate base. So let's go over to the now to the pKa chart here. And so for the first one, we need a acid with a lower pKa than the acetylene. So that would be any acid here that is lower in pKa than that for the acetylene would be a fine acid. These would not work as acids in this reaction. Likewise, the next one was this right here, the conjugate. This was the conjugate acid of the base. So any acid stronger than this one would be a suitable acid for that reaction. The next one was acetic acid, was the conjugate acid of the base. So any acid that is more acidic than the conjugate acid here of that base, which was acetic acid, would be suitable. Lastly, the conjugate acid of our base there was this one right here. So only sulfuric acid would be more acidic than that. And so that's essentially the strategy that you'll use when you look at a base like this, and you decide, okay, what would be a good acid that would actually behave as an acid with this? Well, it's going to have to be a stronger acid than the conjugate acid of the base, so that it could give its proton rather than going in the other direction. Choose a conjugate base from table 3.1 that would effectively deprotonate these. Okay, so these are all acids. So what we need is a base that is stronger than the conjugate base of these acids. So for example, to protonate or to deprotonate hydronium, we would need a base that is stronger than the base water. Okay. And we would need here a base that is stronger than the base chloride, right? For this one here, and so forth. And so, well, how can we figure out, what would be a stronger base than chloride or a stronger base than water? We can go back to the pKa's and just remind ourselves. Remember, the stronger the acid, the weaker the conjugate base. Right, and so chloride ion is a weaker base here than the bisulfite ion, and that means that sulfuric acid would be a stronger acid than chloride. So if we want to protonate chloride, we'd need a stronger acid than HCl. We'd need sulfuric acid. Okay. And so if we want to deprotonate chloride, what would be the base we'd want to use? Well, we want a base that's here, let's see, deprotonate. We'd need any base that is stronger than chloride, right? There's only one base that doesn't fit the bill there, actually, out of the ones on our list anyway. It would be bisulfite would not be suitable for deprotonating HCl. However, any of these bases would. Which includes most any of the conjugate bases of these. And then when it comes to water, we had water. So if we want to, going back, if we wanted to deprotonate hydronium, okay, we need a base here that is stronger than the conjugate base. Water. What would that be? Well, here that would be any of the conjugate bases of these guys right here. Okay, the conjugate base of water is hydroxide. If we want to deprotonate any of these bases that are a stronger base here, then hydroxide would do it just fine, and so forth. So that's the way you compare the relative basicities here. And I'll leave the last couple to you. Now, one important idea here is that if, let's say you're trying to do an acid-base reaction, if your solvent is more acidic than what you're trying to use for an acid, then the solvent is going to be the one that behaves as the acid, not your intended reagent. And if you have a solvent that is a stronger base than your intended base, well, then it will behave as the base. The stronger acid, the stronger base will behave as the acid. This is called the leveling effect on strong acids and bases. So in a lot of these reactions occur in water. So one important consideration is that if an acid is stronger than H3O+, it will react with water to produce H3O+. And then H3O+ will be the acid, not the acid that you intended. If you have a base that is stronger than hydroxide, well, then that base will react with water to produce hydroxide. And so in that case, your base will be hydroxide, not the base that you intended. Okay. So let's take a look here, for example. So we've got, in this case, water would be an appropriate solvent. Okay. And why is that? Well, because if we look for water and we have the acetate ion, if it gets protonated, it produces acetic acid. Okay. So acetic acid here has a pKa of 4.75 and water has a pKa of 15.7. And we know reactions go from stronger acid to weaker acid, and so this reaction is going to go left from stronger acid to weaker acid. So your acetate ion will be preserved and will be able to function as a base. So you can do a reaction where you use acetate ion as a base in water. However, with sulfuric acid, you can not do a reaction with sulfuric acid in water because water will react with it to produce this weaker acid. And this is because sulfuric acid is a stronger acid than the hydronium ion. So if the water takes off the proton and makes hydronium, this hydronium is going to stay. This reaction goes very strongly to the right. And so this hydronium will be what's present in the reaction, not the sulfuric acid. And so this is referred to as the leveling effect. Any acid that's stronger than your solvent will be converted into the conjugate acid of the solvent. And likewise, a base that's stronger than the solvent will be converted into a base, or the conjugate base of the solvent. So, but here's an example right here. This reaction would not work in water. Why? It's because this base, both of these bases, are stronger bases than hydroxide. And so if you put these in water, water's going to react with them and produce hydroxide. We can see that if we go back and we look at this table. So water here, its conjugate base is hydroxide. And the reactant that we had in that reaction was a carbon with a negative charge triple bond to another carbon. And so we can see these are the conjugate acids of these bases. Water is a stronger acid than this acid here, which means, remember, stronger acid, weaker base. So the hydroxide is going to be less basic than this ion here. And so this ion will take the proton from water and produce hydroxide. So you can't use in water, you can't use a base that is stronger than hydroxide because it will convert water into hydroxide instead. And you also cannot use an acid that is stronger than hydronium because it will react with water and produce hydronium instead, and that acid will not remain. This is referred to as the leveling effect of water. And so we can't in the solvent, we can't use a base that is a stronger base than the conjugate base of the solvent, and we can't use an acid that is a stronger acid than the conjugate acid of the solvent. What would be a decent solvent for this? Not water, but any of these where the acid, these are weaker acids, stronger base, right? So the conjugate base would be stronger, not weaker than the base itself. And so, for example, here, if we look at this one, the alcohol. So here, the alcohol is a weaker acid than the water. Therefore, its base is stronger than hydroxide, which makes it work. Yeah, so that's how you decide whether a solvent will work or not. You have to think about, is it going to react with the solvent to produce something else? Then it won't be there anymore. Okay, so that's something to think about. So here's an example where we can't just use REO, though, to compare the relative acidities and basicities of these. Because if we look at the atoms, this proton is attached to the oxygen. If we look for resonance, there is none. If we look for induction, there is none. Orbitals, both of these oxygens are sp3, hybridized. And so we'd have to look at the pKa's here to compare the relative acidities of these. So considering the pKa values measured in solution, how might the solvent act to make the ethanol a stronger acid? So this is where we get another consideration when we're doing the reaction in regards to the solvent. Number one, is there going to be a leveling effect? Is the reactant going to instead react with the solvent and produce the conjugate base of the solvent? And if that conjugate base is a weaker base, well, then the reaction will just go and you'll react with the solvent instead of your target reactant molecule. But then when it comes to the way acids behave in the solution, we also have to think about the relative stability of the anions, right? And that is also going to depend on the solvent. So we've got an anion here. This would be the conjugate base of this acid. And this anion here would be the conjugate base of the acid, the acid ethanol. And now we want to consider, well, remember, for a strong acid, what that means is that the negative charge on its conjugate base is well stabilized, so it can remain that way instead of returning back to the acid form. And so the solvent has a lot to do with this. Looking at this picture here, we can see that when it comes to this ion, which is called ethoxide, the solvent can surround the negative part here to a greater extent than it can in this tert butoxide, as it's called, because there's all these groups out here blocking the interaction of the solvent and the negative part of the ion. And so the result is that the ethoxide is going to be a stronger acid in water than the tert butoxide would be, and in a lot of polar solvents. The reason being because the solvent can greater stabilize and surround this negative ion so that it remains a negative ion, whereas for this sterically crowded ion, the solvent can't surround it as much. So solvation is very important in reactions. The solvent is often used to stabilize the transition states or the intermediates that are produced temporarily while the reaction is happening. And so this can have a huge impact on how acidic or basic a substance will be. For example, acetic acid has a very low pKa in water. It's quite acidic. However, if you put it in this compound, which is essentially basic, its acidity is much less. Why is that? It has to do with the fact that the acetic acid is negative, the water is very positive, and the water can very, very nicely surround the acetate ion that is produced and stabilize that negative charge. And that is done to a significantly lesser extent in this solvent right here, which is not nearly as polar and doesn't have hydrogen bonding and so forth. Also important here are other ions that are in the solutions. Now, often we leave these off. Okay, these are known as counterions, It's because they are usually not going to be involved in the reaction. So we want to leave them off. And that just makes it cleaner and a little bit easier to look at the reaction. For example, here, often when we have a reaction like this, first of all, you can't get ions in a bottle. So you're not going to get this ion here in a bottle, not without its counterion, its positive ion. So if you're performing this in water, let's say, you're going to be dissolving the sodium salt of this reactant, and the sodium ions are going to be there. However, generally group 1 ions are very unreactive. They're very commonly spectator ions. This is something you probably encountered a lot in Chem 151. We did this as well. We generally left off the spectator ions because that just makes things a little bit easier to handle and to analyze. So the sodium ion, is still there in the end, but usually when we draw the reaction, we left it off, and that's the reason why. So the sodium positive ion, it's there. It's also in the products. It's the counterion to this hydroxide ion, but we don't write it because it's not involved in the reaction. And finally, the last topic for this chapter is Lewis acids and bases. And so first of all, the definition. So let's go back and think about the Bronsted-Lowry definition. So I'll call it the BL definition. The BL definition said acid is one that gives or donates H+, and the base is something that accepts the H+. Now, this is a broader definition relative to the Arrhenius definition, which the Arrhenius definition just says a base has to be hydroxide. That's a very narrow definition. We know that there's lots of other bases that we could consider that aren't hydroxide. Anything that accepts a proton. Does hydroxide accept H+? Yeah, when hydroxide accepts H+, it makes water. Likewise, we can have an even broader definition of acid and base, where we say an acid is anything that accepts a pair of electrons, and a base is anything that donates a pair of electrons. And this can describe what we would consider to be BL, Bronsted-Lowry acids and bases, but it can also describe other reactions that don't even have a proton. So for example, here, water is behaving as the base, and HCl is behaving as the acid. The lone pair in the water is attacking the H+, and then the bond electrons here, bonding electrons, are being left behind on the chloride ion. So here, the base is donating a lone pair in order to bond with the H+. And the chloride, the HCl, is accepting the lone pair, right? It's accepting the lone pair because it's being attacked here, and this H+ is grabbing the lone pair. So, or in other words, it's accepting the lone pair too from this bond. And so these are acids, and this is an acid based on the Bronsted-Lowry definition as well. It's donating a proton and the water is accepting it. But it's also, this applies to this broader definition, Lewis acid and base, where the base donates an electron pair and the acid accepts it. Now, what if we have a situation where there's no H+? That can also be described as an acid-base reaction in this definition. So for example, here, the water is donating a lone pair to bond to this boron atom. And so the water here, because it's donating the lone pair, it's considered the base. And the boron trifluoride here is considered the acid. And why does this happen? Why does this happen? Well, in this case, it's because fluorine is so electronegative. It's pulling electrons away from the boron, which makes this center area quite positive. So these electrons are very attracted to that and will go and attack this boron, which is positive. And so even though there's no proton involved, the boron trifluoride can be considered an acid because it's accepting the lone pair. and the water can be considered a base. And this even applies to the very simple Arrhenius definitions of acid and base, H plus and hydroxide. Because if we're drawing a mechanism for this, well, the hydroxide is the base, it is donating the lone pair. So it would be the base. H plus is the acid because it's accepting the lone pair. And the product here, of course, would be water. And so the Lewis acid and base is a broader definition of acid and base that allows us to classify many reactions that would not fall under acid-base in the previous definition. And so in this last lecture, we've discussed the effect of leveling with a solvent, where the solvent can behave as the acid or base if it's incorrectly chosen relative to the reactants. We want the reactants to behave as the acid and base, not the solvent. So we have to be careful that the solvent isn't a stronger acid or base than either of the reactants. And we can do that by comparing the pKa's. In particular, the acid should not be a stronger acid than the conjugate acid of the solvent, and the base should not be a stronger base than the conjugate base of the solvent. Then we described how at acidity and basicity, the pKa's depend on the solvent. The solvent can solvate or surround the ions to differing extents, depending on what the ion is and what the solvent is. And so when that solvent surrounds the ion, it stabilizes that ion, and can a stabilized negative ion, for example, indicates that the acid, the conjugate acid, is a stronger acid. Finally, Lewis acids and bases, as we see here, a Lewis base is a lone pair donor, acid is a lone pair acceptor. And that concludes our acid-base chapter. This is a chapter that will require a lot of practice, so please be sure to try the homework problems and you know complete all the homework problems to get in your practice, so that you'll be ready for the quiz and the exam when it comes. And I hope you guys all have a great week. Bye-bye.